To understand Newton's law of gravitation, which is the main point of chapter 13, we first need to make sure we are clear on a certain mathematical relationship, which is the inverse square relationship. So when we talk about an inverse square relationship, we're talking about something that is proportional to the inverse of something else squared. And in our case specifically, when we're dealing with gravitation, we're going to be dealing with things that are proportional to the inverse of the radius squared. So it's going to be proportional to 1 over r squared, where the radius is how far it is between the center of two objects. So one example of what an inverse square relationship looks like for something that you can actually visualize maybe from your everyday experience is imagine if we took a can of spray paint and we were to fire the nozzle at some screens different distances apart. So we've got our spray paint here, and we're going to spray this at one screen that is somewhat closer. And we could imagine we could spray the paint, and that would hit our screen here, and the paint should be able to cover up that entire screen. We'll get a certain depth of paint, a certain thickness of paint based on how long we hold down the nozzle. If we were to put another screen, though, that was further away, that was twice as far away, so something like here, we can see the paint spreads out. And so in order to catch all of the paint, we would need to have a somewhat larger screen to catch all the paint. And you can see actually the screen, if we are twice as far away, winds up being 4 times the size of our original area because the paint has had twice as long to move up and twice as long to move out. And so it winds up being times 2, so it winds up being 4 times bigger. But the amount of paint that we actually get on here winds up only being a quarter as much in terms of the thickness of the paint because the same amount of paint is going to come out of the spray can, and so while that is going to create a certain depth of paint here, it's only going to have 1/4 of the paint depth here. So if this is area A and this has area 4A, and we've gone to double the radius from our spray can, what we've got here is the same paint spread over 4 times the area, which means that at 2 times the radius, we are going to get 1/4, which is just 1/2 squared the paint thickness. The 1/2 squared is coming from the fact that we've got the paint being spread out, so it's getting half as thick up and down and also half as thick side to side. And so we get 1/2 squared to get a total of 1/4 the paint thickness. And so that is an inverse square relationship. The thickness of the paint that would be left by a spray can on a sheet is inversely proportional to how far away that sheet is from the can of spray paint. And the same relationship, it turns out, has to apply to gravitation, where instead we are talking about how far away an object is from the other object that it is gravitationally attracted to. So we use these inverse square relationships a lot. They are super handy to be comfortable with, not just calculating them through the big gravity formula that you've seen if you've read the chapter. But on free response questions, we need to be able to very, very quickly recognize when an inverse square relationship applies and be able to figure out what's going to happen. And so I just want to write down a couple examples, and hopefully these make sense to you, and hopefully even as I'm saying them, you can recognize what the result is going to be ahead of time. So if we've got an inverse square relationship, that means that our value is going to be proportional to 1 over whatever our radius squared is. So for example, if we have 1/2 of the radius, then the result of that, if there's an inverse square relationship, so if you have half the radius, this is like moving the paper twice as close to the spray can. We're going to get the inverse of this, which is 2 squared is going to be 4 times as large for whatever variable we have that has the inverse square relationship, so the paint thickness or the force of gravity or whatever. And so you can think of this as fractions, where you invert the fraction and then square it. You also can do it in terms of words, in which case we lose the fraction, but we have opposite words. So if the radius is 2 times smaller, that winds up giving us a 4 times larger value. So if we're 2 times smaller on the radius, a smaller radius gives us a larger value, a larger radius gives us a smaller value. So another quick example, if we have 3 times the radius, if we just do it with fractions, the inverse of 3 is 1/3, and 1/3 squared is 1/9. So whatever our thing is that has our inverse square relationship with radius is going to be 1/9 as large. So if it's the paint thickness, if we go 3 times as far away from the spray can, the thickness of the paint is going to be 1/9 as large. Or if we go in terms of gravity, if we go 3 times as far away from the planet or whatever it is that we're being gravitationally attracted to, we'll have 1/9 the force of gravity. And again, we can do this in the words as well. So if we have a 3 times larger radius, then 3 squared is 9 times, and instead of larger it would be a smaller value. And so it doesn't really matter which way you prefer to use. You should be able to interpret both of these, whether they're the more mathematical or the more linguistic representation in terms of if they were like a multiple choice question, and you should be able to show any work that you need to or express your answer in a, if you have to write a sentence or two to justify your answer on the AP test, you should be able to do that. All right, so where this inverse square relationship comes into play with gravity is that there's a problem with the force of gravity equation that we have been using so far. So our old force of gravity equation is the force of gravity is equal to m times g, where m is the mass of the object that we're trying to figure out the force of gravity on, and g is a constant for whatever planet we are on. And I guess the most obvious problem with this is that it changes from planet to planet, which means it obviously doesn't work everywhere. Another problem that is maybe not quite as obvious, though, is that it also doesn't work even for the same planet if you get far enough away from it. So the force of gravity for an object being attracted to the Earth is not always going to be given by this equation. It only works if we are near the surface. So our problem is this equation only works near the surface of the planet. G is being measured for, or G describes. It does not explain gravitation for things that are further out, and it certainly doesn't explain the forces of gravity that we observe between planets that are very far away from each other. And that's actually one of the main ways that Newton would have known that there was a problem with the equation, just based on observations that astronomers had made about the way that planets and stars and other celestial bodies interacted with each other. It didn't make sense. Their motion couldn't be explained by this equation that implied that the force of gravity for an object being attracted to a particular planet was a constant. It was, and we'll talk more about this when we get to Kepler's laws, but from the data you can tell that the force of gravity between the planets has to get smaller as they get further apart. And so we need to figure out a new equation. Newton tried to figured out a new equation, and it had to meet a couple of parameters. It had to accurately work for anything in the universe. It had to explain all the observations that astronomers had made about planetary motion, but it still needed to do what this equation did, which, as long as we were relatively near the surface of the Earth, returned a constant, or a roughly constant value, because that's what we observe near the surface of the planet. So we need a better equation. I can't spell today. We need a better equation, but that equation still needs to return the result that this one gives us, which is still needs to indicate that the force of gravity is approximately equal to m times g and is approximately constant near the surface of a planet, or near the surface of the Earth. So we want an equation that both does what the old equation does, but also better explains all of our planetary interactions, and incorporates this inverse square law, which is the only thing that really explains the observations that a particular astronomer named Kepler made. And so here the history books are not super great about explaining how Newton figured out this equation, although we can sort of make some educated guesses. So Newton was trying to figure out an equation for the force of gravity. And he knew that just based on how objects work when they are near the surface of the Earth, the force of gravity is just directly proportional to the mass of the object that is sitting above the Earth. And so if you triple the mass of the object, it's going to triple the force of gravity. And so any equation for the force of gravity is going to have to still have that be true. And so it's going to have to be directly proportional to the mass, and so I'm going to leave some space here. But the mass of the object sitting on top of the planet, that should be in our equation. Newton's third law also tells us that the force between two objects that are pushing or pulling on each other should be the same for both of them, which means that For example, the force of gravity of the Earth pulling down on you is the exact same as the force of gravity of you pulling up on the Earth. Now, of course, you and the Earth have very different masses, which means that that same force of gravity acting on you and on the Earth does very, very different things. It causes you to accelerate a tremendous amount and causes the Earth to accelerate an amount so small it cannot be measured or observed. But it's still true, and if you brought two objects that were closer in size to each other, maybe a couple of planets or a couple of stars near each other, you should be able to observe a force of gravity for both of them. And the force of gravity should have an observable effect on both of them. Well, Newton's third law says that the force of gravity has to be the same between both of them. And so especially if we had maybe two identically sized stars getting near each other, it would make sense, because Newton's third law is symmetrical, that if the mass of one of the objects, one of the planets, one of the stars, one of the whatevers matters, the other one has to matter as well, because if you have two twin stars near each other and trying to figure out the force of gravity on them, well, we know if doubling the mass of one of those stars is going to double the force of gravity, well, doubling the mass of the other one has to double the force of gravity as well, which means that our force of gravity equation has to be not only directly proportional to the first mass, but also the second mass. And so we know from algebra class, we can set up an equation that is directly proportional to two things by just multiplying them together. It's also got to be true that, based on the observations that an astronomer named Kepler had made and Newton's calculations around those, that the force of gravity has to be following one of our inverse square relationships. It has to be inversely proportional to the square of the distance between the centers of those planets, which we call the radius between the centers of the objects. And so if we want to set up an equation that is inversely proportional to our radius squared, well, then we just divide by the radius squared. And right now this would just be proportional. But these are all the proportionalities. And so the last thing we need for this equation to be true is there just has to be some sort of constant. If this is proportional to this, it just means that this is equal to some constant times this. And so we need a constant, which Newton labeled big G, because it is for gravity in a more universal sense, as opposed to little g, which is referring to just a particular planet. So we've got this equation. Big G is just a constant. M1 and M2, those are required so that we have the symmetry required by the third law. And these are just the masses of the two objects being gravitationally attracted. And that should be in kilograms, because that is our standard unit for mass. And then R is, we'll talk more about exactly when this applies, but if you're dealing with spherical planetary things, it's the center, so I'll say it's roughly the distance between the centers, and we'll talk about when it is and when it isn't exactly that later. So this is roughly the distance between the centers of M1 and M2. And that should be in meters in order for this to work. And this is required in order for our equation to agree with the observations made by the astronomers, particularly Kepler. This equation, it has a number of names. I think in your book, it is just called Newton's law of gravitation. Sometimes it is called the law of universal gravitation or the universal law of gravitation. And since it doesn't really have a standardized name, I wouldn't worry about its name too much. But we need to know that the equation itself exists, and that this is going to tell us the force of gravity between any two objects anywhere in the universe based on just four parameters: the masses of the two objects, how far apart they are, how far apart their centers are, and some sort of constant which is going to apply everywhere in the universe. And what's interesting is that Newton never knew what big G was the entire time he was alive. It wasn't actually until significantly later that he was able to solve for it. And yet the equation is still true. And his reasoning was correct, and it would have to be, because if it's got to be directly proportional to these two things and inversely proportional to the radius squared, then it's got to be some sort of constant times these, even if he didn't know what it was. So let's verify that this actually does what it's supposed to. We said that the equation has to return a force of gravity value that is roughly constant near the surface of a planet. And when we were... And we know specifically that this has to return something that's roughly equal to m times g as well, if we're dealing with the Earth. We used the force of gravity equals m times g a whole lot when we were dealing with the Earth, and we didn't really care if we were falling out of an airplane, on top of a mountain, in a skyscraper, or just standing on the surface of the Earth. We never had the force of gravity go down when we were further away, like this equation would imply. And so let's take a look at why that is and make sure that this equation really does return a roughly constant value anywhere near the surface of the Earth. And we're going to define anywhere near the surface of the Earth as like within a plane trip, within a mountain height, anything sort of like that of the surface of the Earth. So what I would like you to try to figure out is if we assume that the radius of the Earth is about 6.37 times 10 to the sixth meters, so that's 6,370,000 meters. And I say approximately because the Earth's not actually perfectly spherical. And so it's kind of like wider in the middle, and so the radius of the Earth at the equator is bigger than this, and the radius of the Earth at the poles is smaller than this. But we are just going to pretend the Earth is a sphere, and it's pretty close to a sphere, and this is sort of like a nice median value in between. So we're gonna use this as roughly the radius of the Earth. It's gonna get us close. It's gonna get us within a sig fig, which is fine. So you can assume that that's the radius of the Earth. If you're just standing on the surface of the Earth, that's what we got. And if you go to the top of the highest point on the Earth, which would be the top of Mount Everest, the height of Mount Everest is equal to roughly 8,850 meters, so almost 9 kilometers, so several miles up. And we want to figure out how much smaller the force of gravity is at the top of Mount Everest versus the surface of the Earth. So how much smaller is the force of gravity at the top of Everest versus at the surface of the Earth. We don't have actual numbers here, of course. You don't know the mass of the other object. I haven't told you the mass of the Earth yet. I haven't even told you what big G is. And so you're going to solve this either as a percent or as a ratio. So what I'd like you to do is go ahead and pause the video for a few minutes and try to solve this problem and see what you come up with. All right, so you can go ahead and check your work here. So we're trying to figure out, what our ratio is. And so we could say, and there's a few different ways to do this. You'll be able to tell if your answer's on the right order of magnitude. So the force of gravity at the top of Everest is going to be equal to, we just take our, Newton's law of gravitation, GMM over R squared. We don't actually know what G is yet. We don't know either of the masses we're dealing with. We do know that the radius, though, is going to be Mount Everest plus the Earth. So that's going to be 6,370,000 plus 8,850 squared. And then if we want to find like a ratio, for example, it would be divided by the force of gravity at the surface. So that's going to be, we'll divide by G times M1 times M2 divided by just the radius of the Earth, because that's going to tell us how far it is. The radius of the Earth is going to go, from the center of the Earth to our object that's standing on the surface of the Earth. So that's going to be 6,370,000 squared. And so you can see all of this stuff cancels out. And so we just wind up with a ratio here that we don't need to know any of the actual constants for. This comes out to be about 0.9972, which we can interpret as the force of gravity is about 0.28% smaller on Everest, which is not much of a change. And so that is consistent with the way we've been using our force of gravity equation, where we've just assumed that it returns a constant value. And so this is indeed approximately constant. Whether we are on the surface of the Earth or we're on Everest, the force of gravity anywhere near the surface of the Earth, anywhere that people can go on their own, anywhere that most planes can go, is basically constant. And so our simpler equation, this one, force of gravity equals mg, that's fine. That is just fine as long as you are dealing with things that are, earthbound objects and things that people interact with in their everyday life if they are not astronauts. And this is the equation you should use if we are dealing with stuff that does not apply to, anything on sort of like outer space or planet, like interplanetary sort of scale. But also, if you really want to, you can always use this equation too. It will always work. It is just more complicated and overkill than the other one if you're dealing with stuff on the surface of the Earth. The next thing that we should actually do is we should figure out what G is. And so the first thing I'd like you to actually do is to figure out just what the units for G have to be. So what units does our big G, our gravitation constant, have to have? And so, again, I'll just write the equation here. So the force of gravity is given by whatever this big G is, times m1 times m2, divided by the radius, the distance between our objects squared. And so, once again, I'd like you to pause the video and just try to figure out what unit G has to have in order for that equation to work. So go ahead and do that. Okay, so if we just solve this for big G, we're going to have Fg times the radius squared divided by m1 divided by m2. And so the units there, the force of gravity is, of course, measured in newtons. The radius is measured in meters. The radius squared is meters squared. And the masses are each measured in kilograms. So m1 times m2 is going to be kilograms squared. And so we could certainly leave it as Newton meters squared per kilogram squared. That's fine. We could also break this down. A Newton is the same as a kilogram meter per second squared. We're then going to multiply that by meters squared and divide by kilograms squared. So we'll cancel out a kilogram, and we will get meters cubed per kilogram seconds squared. And so those are they're both okay because they're both mean the same thing. And then the actual number for G, which you can always look up in a book if you need it. It is on the AP equation sheet, but the actual constant, which you will need for a lot of our problems, is 6.67 times 10 to the negative 11th. And that's going to be in, either one of these units. So Newton meters squared per kilogram squared, or meters cubed per kilogram second squared, whatever you prefer.